Hello everyone. My name is Yaoshu Wang, and I am a researcher in Shenzhen Institute of Computing Science, Shenzhen University. And today, the paper I'm presenting now is titled "Consistent and Flexible Selectivity Estimation for high-dimensional data." So first, I will introduce the problem definition. Given a data set D consisting of high-dimensional vectors, a distant function fd, a query vector q, and a predefined threshold tau. So we aim to estimate the cardinality of results such that we find the number of data in the dataset whose distance with query is no larger than the threshold. So in this page, I gave an example of image retrieval. Firstly, we have a query image, and we want to find the number of similar images in the database. We can use the FaceNet model, a state-of-art computer vision model, to transfer it into an embedding, and use some distance functions such as Euclidean distance or a cosine distance to find similar images. So in this example, the cardinality of the query Q is 3. We can also use Hamming distance instead of Euclidean or cosine distance. In this example, we want to find the data in the database whose Hamming distance is within the threshold 3. So we can find the results is the cardinality value is 2. Okay, here I will discuss the applications. One application of selectivity estimation is query optimization. Some approximate query processing methods needs the query optimization to accelerate the procedure. For example, in an ICD paper, GPH adopts the dynamic programming method to find the optimal threshold allocation for approximate query processing in the Hamming space. Here in the dynamic programming procedure, one important step here is to get the selectivity values of each partition with different thresholds. When the dimensions of the data set is very high, I think it is not feasible to store the selectivity values of all situations, such as all combinations of binary codes. So in this page, shows the procedure of dynamic programming. We can see that in the yellow region is the selectivity value of different thresholds for the same query. Here we can use a machine learning model to estimate it. The second application is density estimation. It is important to find the correlation and popularity among words, topic, movies, and so forth. So in this example, we have a lot of movie titles. We can use some neural networks, some state-of-art models to transfer each titles into embedding, and we can use selective estimation to estimate the number of similar movies of a query. Okay. And now I will discuss the importance of monotonicity. Recall that we need dynamic programming to solve the threshold allocation problem. So in this page, for the same query, the selectivity of a smaller threshold should be no larger than the selectivity of a large threshold. Okay, if it is not feasible, dynamic programming will not make sense. So I think the monotonic property makes sure that the dynamic programming can have the correct answer. Okay, the second application is the density estimation. So users always expect to find more results if they lose the threshold. So if they change the threshold from such as 0.1 to 0.5, they always expect to get the more result size. Okay, in the existing words, I mainly classify them into 4 categories. In the first category, there are 2 methods for traditional methods. So in the low dimensional data, a histogram is widely used, but it is a bit hard to find the optimal histogram if the dimension is larger than 2. A sampling method is also used, and it has theoretical guarantees, such as random sampling and importance sampling. The second category is machine learning-based models. Kernel density animation is widely used for selectivity estimations, and its main idea is to use uniform sampling with some smoothing methods. Also, some regression models such as SVM, random forest boosting tree, can be used to predict the selectivity values. We can first generate some training data, such as one training instance is a pair of query and its result size. And then we can use a supervised learning manner to train a regression model. And then we can use this model to predict the selectivity. The third category is deep learning methods. Also, they can also use for they can also use for the regression to predict the selectivity. From my understanding, I think the main advantage of deep learning model is that they have the ability to deal with high dimensionality. But I think it might be not good to directly use them as black box. The final category is the monotonic models. There are few deep learning methods to achieve the monotonity. Because they always, in most of models, they impose some monotonic constraints to their parameters, but this behavior will reduce the flexibility of these models. Okay, and now I will introduce our selectivity estimator CellNet. Okay, first I will discuss two observations. The first observation is that we can partition the threshold of the selectivity. So the naive way is that we need to learn the selectivity of a query and the threshold. But I think one promising way is to partition the threshold into several parts and then separately learn them. For you can see in the figure, if instead of running the selectivity of tau max for a particular query, we can partition the tau max into several segments, and then we run the incremental selectivities with some neural networks for machine learning models. The second observation is that the domain of selectivity may be very large. So the maximum value of selectivity is the number of data in the data set. So to solve that, we can also partition the data set D into several non-overlapping parts, and then for each part we use a machine learning model to run the local selectivities, and finally we sum up all these local selectivities and then get the final selectivity of the whole data set. Okay, now we introduce the model, our model CellNet, and we heavily use the piecewise linear function for our model. So in this page, we can see that in this page we can see a figure which shows the selectivity values with threshold. So the blue curve shows the changes of selectivity values as the threshold of one particular query increase. So here we assume the domain of selectivity is 0 to 10. You can see that the 0 to 10. So the 0 is the minimal threshold and 10 is the maximal threshold, which is given by users in the pre-processing steps. So one simple way to use piecewise linear function is to uniformly partition the threshold domain. Such as in this figure, in this example, we partition the domain into 5 segments. Here we call the splitting points, the red points, as the control point. Therefore, if we have the 5 segments, and then we also got 6 control points, 1, 2, 3, 4, 5, 6 control points, and then we can learn the selectivity of each control points. But so this is the simple piecewise linear function. But we can see that the piecewise linear function in some segments cannot fit blue curves well. So, for example, in a segment of threshold between 8 and 10, the gap between the ground truth and the prediction is large. So maybe we can use a method to learn the control point instead of uniformly sampling it. Here we use a neural network to learn the positions, such as the positions of control points. We mainly use 2 ideas. Firstly, we can learn the position of thresholds instead of uniform partition. So see the left figure, we aim to find good positions of control points, such that in each segment, the linear function is able to fit the curve well. So secondly, we observe that different queries should have the different curves of selectivities. So compare with the 2 figures of 2 different queries, and their curves of selectivity are different. So we can conclude that the control points are dependent with the input query points. So here, based on 2 ideas, we designed the function norm, the norm function, to partition the threshold domain. Now, firstly, the partitioning is learned during training, so that the partition is inclined to find a good control point, such that a linear function in each segment can fit the curve well. And secondly, we can see that the function norm is dependent with the query. The function norm is dependent with the query x, so that different query x have different partitions. And then after the control points are fixed, we are able to learn the incremental selectivity between 2 adjacent control points, such that we can learn the incremental between these 2 control points. Here, to make sure that our selectivity estimator is consistent or monotonic, we use the ReLU activation function. We use ReLU function to make sure that each incremental selectivity is non-negative. Therefore, our selectivity estimator is consistent with respect to the threshold. Okay, finally, I discussed our model architecture. So this figure shows the model structure of a cell net. The inputs are 2 factors: the query vector x and the given threshold t. So firstly, we use an autoencoder to learn the latent representation z of a query, and then we concatenate these 2 vectors into a new one, and transfer them to 2 separate components, a feed-forward network and a model M. So the feed-forward network learns the threshold partition for different queries, and the model M is to learn the incremental selectivity of these control points. So the model M is also based on the feed-forward neural networks. So with the input x and z, and we learned R+2 embeddings of control points, and for each control points, and we use the linear model and with ReLU activation function to get incremental selectivities, and the ReLU makes sure that the Ki is non-negative. So finally, and we use the piecewise linear function to combine these 2 components, and to get the final selectivity with respect to the given threshold t and the query vector x. So because the ReLU makes sure that the incremental selectivity is non-negative, so the final prediction y is monotonic with t and with different t and the same x. So in this page, I will show the data partitioning of our model. Here we use the color tree to partition D into several parts, and then we use the greedy method to merge some small parts so that the all parts all partitions have a similar size. Finally, and we use different separate models to learn the local selectivities for each part, and then we sum them up to get the final selectivity values. So here, make sure for the red point is the query. So we can see that with the given threshold, and the red circle is the query region. So we only need to consider partition that has overlap with the query region. Finally, I will introduce our function. The first term is the Hilbert loss of the global selectivity and the global prediction. The second term is the Hilbert loss of the all local selectivities and all local predictions, and we sum this local loss up. Sum up of this local loss. The third term is the loss of autoencoders. And we sum up these three terms, and we get the final loss functions for our models. So here in the experimental section, and we use 6 data sets, and we compare with several methods with 4 categories, such as for DB methods, we compare with random sampling, important sampling. And for machine learning models, I will compare with LightGBM and KDE. In the deep learning models, we compare with mixture of expert model, RMI, and feed-forward network. And finally, we compare with some monotonic models, DRN, UMN, and CarNet. So our model is CellNet. We tested the accuracy in 4 data sets, and with 3 mixtures, MSE, MAE, and MAPE. And in this table, we find that deep learning methods, most deep learning methods performs well, and because our method considered the threshold partition and the data partition, so CellNet achieved the best performance. This table shows the accuracy of 2 large data sets, and we can see that our model still achieved the best performance. This table shows the average estimation time of different methods in 6 data sets. So the feed-forward neural network is the fastest because it's simple architecture. So compared with exact similarity search, such as color tree methods, the machine learning models are much faster. Finally, we make some conclusions. First, we adopt deep learning-based models to solve the selectivity estimation and show it is a successful direction. Secondly, we propose a kinetic estimation model that is consistent with respect to threshold. Thirdly, we propose an idea of learning the piecewise linear function in a query-driven manner, such that the estimation is consistent, accurate, and fast. Finally, we design a comprehensive experiment to show the faster estimation time and small errors of our models. Thank you, everyone. This is all my presentation.